Up to this point, we've talked about our noise figure and our effective input temperature for active components, for amplifiers, but this idea can also be extended to passive components. And so the reason that's going to be important is that our passive components can also degrade our signal to noise ratio. The most common example would be if we think about just simple cabling. So maybe connecting our antenna to our various amplifiers, we're going to need some cabling. And if our antenna is up on a large tower, we might have a significant amount of cabling that can reduce our signal or attenuate our signal as it travels through that cable. So we want a way to sort of quantify how much that cabling, or that, to be more general, that passive component is going to degrade our signal to noise ratio. So we're not going to get into a lengthy derivation, we're just going to sort of give the results here. But using thermodynamics, we could show that our effective input temperature of some passive element is equal to T sub A times 1 minus 1 over L. So let's define a couple of these new terms here. So of course this T sub E we set as our effective input temperature. Our T sub A is just the ambient temperature of the system or of the circuit. So this is our ambient temp. So if we're talking about cabling, then that's just the temperature where the cable is. Our L is something called our loss ratio. And so our loss ratio is defined as power in divided by power out. And so oftentimes this loss ratio will just be given for a certain element, but we could also go back to this more basic equation of P in over P out to determine that, and then from that determine our effective input temperature, T sub E. So let's consider some extreme cases to sort of get a better idea of what our possible L values are. So extreme cases. So our first one would be L equals 1. And so looking at this equation, we can say L equals 1 corresponds to where all of our power in has become power out. So we can sort of say this is going to be our best case. We've not lost any power going through this passive element. And so what that means for our effective input temperature, coming back up to this equation, we can see we have in parentheses on the right side 1 minus 1 over L. Well, if our L is 1, that term in parentheses just becomes 0, and our effective input temperature of our passive component is equal to 0. And so this, of course, corresponds to when we considered earlier, for instance, our noiseless amplifiers. So our other extreme case would be as our L gets really large, so as our L goes to infinity. And coming back up to this equation, we can see that would correspond to this P out getting really small. So this is sort of our worst case, as we're losing sort of almost all of that input power and none of it is becoming output power. Coming back up here to our effective input temperature equation, we see if we have a really large L on the right-hand side, we're essentially just going to have 1 times TA. So that means that our effective input temperature is just going to be the ambient temperature. So this T sub E for our passive element is approaching, so since we're saying this is approaching infinity, this is going to be approaching a temperature of TA, which again, remember, is our ambient temperature. So these are sort of the two extremes in terms of our loss ratio. And so of course from there, if we have this sort of cascaded in a system between amplifiers, for instance, we would use this effective input temperature the same way we did where we talked about cascading several op amps. So in the next videos, we're going to do just that. We're going to look at a very detailed example of a communication a link, and we're going to look at our amplifiers, our components, and we're going to see how we can design that to work how we want.